Our sun is likely a second or third generation star, formed from the leftover gas and dust of stars that had already died. Every living creature, the air we breathe, and the water we drink are made of atoms first forged inside stars. In that sense, we are all made of star stuff. But this notion, which connects us so intimately to the cosmos, may only be part of the story. Recent discoveries hint at an even deeper and more unsettling idea. Stars may not only create the matter that makes up living things, they might also be responsible for the creation, evolution, and extinction of life wherever it arises in the universe. Yet how can stars, so distant and remote, be associated with our lives? What cosmic bond links us to them? To find answers, we embark on a journey through some of the world's foremost research centers, a quest that leads us into a hidden natural phenomenon: cosmic radiation, where astronomy intersects with particle physics and biology. In exploring cosmic radiation, we search for the tie between life on Earth and the most distant stars. Perhaps stars have contributed more than just the atoms we are made of. Perhaps we are not merely star stuff. Our first stop is Calar Alto Observatory in southern Spain, operated by German and Spanish astronomers. Blessed with dry, sunny weather and clear skies, this mountainous region offers ideal viewing conditions. Here, astronomers like Anne use telescopes collecting visible and infrared starlight to unravel how stars produce the chemical elements. With the telescopes at Calar Alto, Anne explains, we can analyze what stars are made of, which elements they contain, and which ones they're forming. Through 20th century astronomy, scientists learned that stars, like living things, have life cycles: birth, life, and death. Vast cosmic clouds of gas and dust accumulate, drawn together by gravity, until the temperature and pressure grow so immense that hydrogen fuses into helium. Further nuclear fusion produces heavier atoms: carbon, oxygen, silicon, iron. Near the end of a star's life, colossal blasts known as novae or supernovae hurl these newly minted elements back into space. Those stellar remains eventually form new stars, planets, and everything on them. Thus, our own sun is not a first-generation star. It coalesced from an enriched medium of previously forged stardust. This leads to a disquieting, yet awe-inspiring idea. We truly are part of the cosmos. The atoms in Earth's living beings were once inside stars. We are star stuff, as Carl Sagan famously said. But modern science indicates our stellar ties run deeper still. When stars die, they not only release atoms, but also hurl out vast numbers of energetic particles called cosmic rays. These subatomic cosmic bullets may play a role in creating, fostering, and even ending life across the universe. Cosmic rays, despite their name, are not rays of light. They are tiny fragments of matter, mainly protons and nuclei, launched at near light speed from violent cosmic events such as supernovae or black holes, or from our own sun. Because they're invisible, no conventional telescope can see them. Detecting cosmic rays requires instruments that can sense subatomic particles streaking into our atmosphere. In a small lab, we see a spark chamber, a device that makes cosmic rays briefly visible. When a charged particle passes through, it triggers a flash of pinkish sparks, revealing its path. Oddly, no one fires these particles into the chamber. They arrive constantly from space. Regardless of whether you're in a city, a desert, or at the poles, cosmic rays rain down ceaselessly. You can't hide from them unless you dig deep underground, because they pass easily through rock, water, even human bodies. The spark chamber proves they're always here, though normally imperceptible. Historically, cosmic rays were discovered by pure chance. In the early 1900s, scientists noticed that electroscopes, devices with metal leaves that spread apart when charged, mysteriously lost charge over time. They suspected Earth's natural radioactivity might be responsible, so they carried electroscopes up towers and in hot air balloons to measure discharge rates. Surprising results, faster discharge higher up, pointed to a source beyond Earth. Thus was born cosmic ray astronomy. Jump to the 21st century, to the Pierre Auger Observatory in Mendoza, Argentina. The largest cosmic ray detector in the world, covering an area larger than many cities. It consists of 1,660 water tanks spread across 3,000 square kilometers, supplemented by 4 fluorescence buildings that watch for faint flashes of light in the sky. Pavel, one of the scientists, explains how most cosmic rays are protons, about 90%, the rest being helium nuclei, electrons, or heavier nuclei like iron or nitrogen. Their energies range from low, solar origin, through medium, probably supernova remnants in our galaxy, to extremely high, possibly arising from active galactic nuclei far beyond the Milky Way. While low-energy solar cosmic rays are deflected toward Earth's poles, giving us the beautiful auroras, high-energy cosmic rays plow straight through Earth's magnetic field. When they crash into our atmosphere, they create air showers, cascades of secondary particles that extend over many square kilometers. The Pierre Auger Observatory detects these showers 2 ways: surface detectors, water tanks. Particles from cosmic ray collisions pass through each tank, where specialized sensors read out signals. Fluorescence detectors, high above the tanks, large mirrors and photosensors capture faint flashes from excited atmospheric molecules along the shower's path. Using both methods in tandem yields extreme precision. Scientists have definitively proved that Earth is awash in cosmic rays, subatomic messengers from distant stars. So cosmic rays fill space, racing along at nearly light speed. They also traverse giant molecular clouds, vast regions of dust and gas from which new stars and planets form. At the Astrobiology Center near Madrid, Guillermo simulates these clouds, replicating their chilling vacuum conditions to study how the simplest molecules might become seeds for life. Inside dense molecular clouds, a protective shell of dust and ice shields matter from starlight. But cosmic rays, carrying tremendous energy, penetrate easily, sparking chemical reactions on dust-grain surfaces that build complex prebiotic molecules, amino acid precursors, sugar-related substances, etc. Yet there's still the question of how these molecules reach a planet. As a star forms, extreme heat typically destroys them, unless they hide in comets and asteroids, which remain cooler and thus preserve their precious cargo. Later, these bodies can deliver the molecules onto habitable worlds. Indeed, meteorites that have fallen to Earth contain over 100 amino acids, compared to just 20 in modern Earth biology. Many are formed in interstellar space, propelled here by cosmic collisions. Excitingly, the ESA's Rosetta mission confirmed such molecules on a comet, 16 organics, some essential for life's origins, collected by pure luck during a landing mishap. This discovery hints that similar processes occur all across the cosmos. Where Earth-like planets exist, comets might ferry the seeds of life onto their surfaces. That implies life could be a universal phenomenon. Cosmic rays also influence Earth's atmosphere. In Switzerland, Jasper Kirkby's experiment known as Cloud at CERN seeks to uncover how cosmic rays shape cloud formation. The atmosphere, vital for life, owes its circulation to sunlight, warming the oceans and land. But scientists also note correlations between solar activity and Earth's climate, suggesting distant stars might play a role. When cosmic rays penetrate the atmosphere, explains Jasper, they ionize the air, creating tiny embryonic seeds. These droplets or particles can grow into full-fledged cloud condensation nuclei. If cosmic rays significantly affect cloud formation, they might regulate global temperature and precipitation over geological timescales, thus impacting the emergence or survival of life. Although these findings are not definitive yet, the research is thrilling. Cloud is the only experiment of its kind, testing how simulated atmospheres respond to a controlled beam of protons. It's also exploring a second phenomenon. Cosmic rays help maintain the Earth's global electrical circuit, crucial to lightning production. Lightning discharges likely helped create the first amino acids and other biomolecules on primordial Earth. Once more, cosmic rays appear as a cosmic spark that can trigger life-friendly chemistry. Our final stop returns us to the Astrobiology Center in Madrid, where Eduardo studies how cosmic rays might help shape the evolution of life itself. Earth's biosphere arose roughly 3.8 billion years ago. Over countless generations, DNA replication errors, mutations, enabled diversity to flourish. Some mutations result from naturally occurring radioactive materials in Earth's crust, but cosmic rays also bombard DNA, causing breaks or rearrangements that can spark new traits. Perhaps in Earth's distant past, Eduardo posits, massive cosmic ray surges from supernova explosions or extreme solar events accelerated evolutionary processes. Such ideas remain hypothetical, but new research combining DNA sequencing, astrophysics, and cosmic ray detection might soon measure mutation rates under different cosmic ray exposures, offering deeper insights into cosmic rays' evolutionary impact. Our journey ends, having traced the path of the universe's most energetic particles. We found cosmic rays forging complex molecules in freezing interstellar clouds, possibly delivering these precursors to nascent planets. We saw how cosmic rays trigger lightning, contribute to cloud formation, and perhaps accelerate genetic changes that spawn biological innovation. We often hear, "We are star stuff." The stars created our atoms, flung them into space, and shaped our solar system. Yet evidence now suggests stars, through cosmic rays, keep influencing us, fueling life's origins, driving climates, and nudging DNA toward new frontiers. Every time a star dies, its explosive energy rides cosmic beams across the cosmos, potentially igniting the spark of life on unknown worlds. Thus, stars do not merely birth our matter and vanish. They continue to guide, sustain, and perhaps even extinguish life across the vast tapestry of the universe. The story of cosmic rays, and our deep bond with the stars, continues, calling new explorers to discover how these distant stellar furnaces quietly shape life here and beyond.